Hello, Dr. Rashma. How are you? This is my presentation for unit number two, and the building that I chose for this unit is the Taipei 101. So, this is the Taipei 101. It is a benchmark in modern high rise construction completed in 2004. This 509-meter super tall tower in Taiwan is not just the country's most famous landmark, it is also a masterpiece of civil engineering which successfully fights earthquakes and typhoons while achieving top level sustainability. Let's see how it became a global reference. So, Taipei 101 raises 101 stories and 509 meters, making it the world's tallest building from 2004 to 2010. Of course, the crown now is worn by the Burj Khalifa. This tower it's a mixed use tower. Offices, retail, restaurants, and an observatory. The biggest challenge Taiwan is hit by several typhoons, I don't know how to say it, every year and sits on one of the most active seismic zones in the world. From day one, the design team had to guarantee safety, comfort, and sustainability under extreme conditions. That's exactly what makes Taipei 101 a perfect real world case study for our unit. In construction, we normally talk about four main types: residential, commercial, industrial, and infrastructure. Residential focuses on comfort and low cost, industrial on functionality and heavy loads, infrastructure on durability against nature, and Taipei 101 is classified as commercial mixed use, but it borrows the extreme durability of infrastructure projects and the structural strength we usually see in industrial facilities. In short, it is a hybrid that breaks traditional categories, and that's one reason it is so innovative. Sustainability achievements. Sustainability was a priority from the beginning. In 2011, Taipei 101 became the world's tallest building to achieve LEED Platinum, and it has renewed that certification in 2016 and 2021. Key features include a double skin facade that reduces solar heat gain, high performance concrete with fly ash, advanced HVAC, and lining controls, and rainwater harvesting. The result: 30% less potable water consumption. That's 28 million liters saved every year, and 80% of operational waste recycled for a humid subtropical climate. These numbers are outstanding. Crazy. Risk management and health and safety. Building a 509-meter tower in a seismic zone is inherently high risk. The team used intensive computer simulations, multiple structural redundancies, and the famous 660-ton tuned mass damper, still one of the largest ever built. During construction, they followed Taiwan's strict Occupational Safety and Health Act. Full body harnesses, dust suppression, fatigue management, and real monitoring. The result was remarkable. Almost almost zero serious accidents on a project of this scale. And the building has survived several magnitude 7 earthquake and category 5 typhoons with virtually no structural damage. Incredible. Pre-design studies and site conditions. Before the first shovel touched the ground, 2 years of studies were carried out. Soil borings revealed soft alluvial clay in a fold only 200 meters away. Seismic and wind tunnels tests simulated magnitude 7 earthquakes and 100 miles per hour typhoon winds. Groundwater was only 5 or 10 meters deep, so flooding risk was high. All this data forced the engineers to go for very deep foundations and a top down construction method. Decisions that were 100% driven by the site investigation results. Substructure design and works. The substructure is impressive. 380 concrete piles, each 1.5 meters in diameter, driven up to 80 meters into bedrock. On top sits a 3 to 5 meter thick mud foundation to keep the excavation dry in that high water table. 35-meter deep shuri walls were built first, allowing top down construction of the five basement levels. Soil was stabilized by grouting, and dewatering lowered the water table by 10 meters. This is civil engineering at infrastructure scale applied to a skyscraper. Superstructure and structural frame. The superstructure uses a steel concrete megaframe with 16 giant mega columns, a brace core, and outrigger trusses every 8 floors. This system gives enormous lateral stiffness against wind and earthquakes. Compared to tube frames, the grid of the buttressed core of Burj Khalifa, the mega frame offered the best combination of open floor plates, material efficiency, and seismic ductility for Taipei's conditions. And of course, the 660 tone tuned mass damper between floors 87 and 92 reduces sway by up to 40%. Primary services, supply, distribution, and integration. Primary services are fully integrated into the structural design. Electrical risers run inside the concrete field core. Chilled water pipes and earth ducts use the mechanical floors where the outriggers are located. Water is pumped in zones with pressure reducing valves. This clever layout means services do not steal rentable space and are protected during earthquakes. The result is 25% lower energy losses compared to traditional distribution, again helping the LEED score. Conclusion and recommendations. Taipei 101 proves that safety, sustainability, and architectural ambition can go together. Key lessons: hybrid megaframes work brilliantly in seismic zones. Early site investigation saves money later, and services integration from day one improves both performance and aesthetics. My top 5 recommendations for future super tools are: first, use AI driven predictive monitoring from the design phase. Second, increase prefabrication of outriggers and core elements. Third, move toward circular economy materials. Fourth, involve MEP engineers from concept stage. And the fifth one is make post occupancy evaluation mandatory. And to finalize, 20 years after completion, Taipei 101 remains a global reference for resilient, sustainable, and safe high rise construction. Thank you so much.